All right. Good morning, everyone. Glad to see everyone made it after the Labor Day weekend. Welcome to today's webinar, How Stencil Manufacturing Methods Impact Precision and Accuracy. Today's webinar is based off a white paper written by Anna Osterhoff of Osterhoff Consulting and Stefan Schmidt, president of LPKF North America. We are live here in Portland, Oregon at LPKF Studios, and today's webinar is a must-see for anyone involved in the SMT stencil manufacturing or buying process. My name is Shane. I'm in the marketing department here in Portland, and I'm joined today by the esteemed Mr. Osterhoff himself. Now, Anna is an expert in the stencil manufacturing industry. He served many years as engineering manager at Tektronix, founded the company A-Laser, and serves as an independent consultant on all matters related to SMT stencils. If you have any questions throughout today's webinar, feel free to submit them via GoTo's question submit form as seen there on your screen. Or you can even submit them via Twitter. You can do this by tweeting your question with the hashtag LPKF, or you can tweet directly to @LPKF_USA. We will field questions at the end of today's presentation. So I'd like to open up today by giving you an old quote, which is, "I can make a bad stencil on any laser and a good stencil only on some lasers." You're telling me, the man says. So this brings a number of questions to mind. What exactly is a good stencil? What type of laser do I need to get there? Or even, how well do my supplier's methods work? Now, these are all things to consider when going through the stencil process. So one of the questions I just mentioned was, how do you know what is a good stencil? So I thought I'd let you guys decide. I'm going to launch a poll, and I want you to tell me, what is the most important factor in manufacturing a good stencil? I will open up the poll right now. So you should be able to see there on your screen. So we'll go ahead and leave it open for just a minute. And if you want to, go ahead and select your answer. It looks like almost everyone has voted. Oh, that's it. Everyone's voted. So we'll go ahead and close the poll, and we're going to review the results. So Anna, looks like we have smooth sidewalls for good paste release coming in first, followed by consistent aperture dimensions, and then a tie for correct aperture location and straight and accurate aperture sidewalls. So Anna, why don't you tell me what is your answer for the poll?
The first thing I would consider is the paste has to land on the pad. So the stencil has to be accurate, precise, and which is what this presentation is going to be all about. Secondly, you need the right amount of paste. So the aperture has to be the right size, etc. Thirdly, the paste has to come out of the aperture, so sidewalls have to be relatively clean and straight so that the paste can be released. 4 is the A, which has to be, the stencil has to be consistent in thickness, so you get the right amount of paste from any aperture. And finally, you want straight and accurate aperture sidewalls, which that helps in the paste release, which is D.
Awesome. Okay. Let's head on to the next after the poll. So you just talked about what was the most important. Now there's 4 things which really influence the accuracy and manufacturing a good stencil. And these are the 4 M's. So Anna, why don't you tell me a little bit about the 4 M's?
The 4 M's are essentially machines, methods, manpower, and materials. And what that means is that the machines have to be of the appropriate quality to make good stencils. The methods, you need a process in place that allows the machine to do it correctly, and the manpower, the next one, has to be well educated, well trained to use the machines and everything else appropriately. And lastly, the materials that you're using have to be of a good enough quality to make good stencils. Additionally, there are some factors that impact a good stencil, and that is temperature differences during the process and changes in tension on the material, on the metal that is used to make the stencil. And I'll explain that in the rest of the seminar.
Awesome. Thanks, Anna. So I just wanted to introduce the topics we'll be covering today. First, we're going to look at a brief history of stencil manufacturing technologies and how they've progressed. Secondly, we're going to break down the two most prevalent stencil manufacturing technologies of today. As Anna just mentioned, the effects of tension and temperature kind of sneak up on you. And so we'll look at how those affect the manufacturing process for stencils. And then finally, we're going to take a look at CP analysis of 13 different laser cut stencils and one electroformed stencil. But first, let's start at the beginning because that's always a very good place to start. So Anna, get us going on the history of stencil manufacturing methods.
Initially, the first stencils way back were essentially a silk screen, and as the components that were being used got smaller and smaller, the aperture became smaller, and the wires in the silk screen got in the way of releasing the paste. So it was necessary to find different process. The next step after that was to make chemically etched stencils. Chemically etched stencils use a film to transfer the image to the metal, and then the etchant cuts the hole in the metal. The problem with that is that the etchant not only cuts down into the metal but also sideways, so you end up with a cup-shaped aperture. That was not very desirable, so the next step was to etch from both sides using two films. But depending on the control of the process, it could leave a ridge in the middle of the metal. And on this image, you can see that ridge clearly. To improve on that, electroforming became the next process. And in this process, the metal is grown on a mandrel, and you get a nice sidewalls to enhance paste release. Besides that, the metal is almost always nickel, which releases the paste a little bit better than just straight stainless steel. Here's an example of the electroformed sidewalls, and you can see it does have striations, but those are all in line with the paste release, so paste release is pretty good. Next step to make the process faster and simpler was to go to laser cut stencils. And we'll review both the electroforming and the laser cutting process a little bit more after this. Here's a picture of an original or early laser cut stencil. Again, there are striations in the metal due to the pulsing and melting of the metal, but the paste release typically has been pretty good. To show essentially what a laser does, it is pulsing, and each pulse cuts a little bit of the metal away. What I have in the picture here is showing a number of methods to cut paper. The first one is the corner of a postage stamp. and the apertures are the pulses from the laser, if that was a laser, are far apart, and obviously that is not going to cut metal. The next one is laser cut paper, and obviously the cuts are much closer together and they form a continuous line even though it's a scalloped line. The third one is a knife cut piece of paper, and that's the kind of sidewall that you would like to see in the apertures in the metal. So the pulses are very close together and you end up with a straight line. The newest laser are diode pumped, which gives you much higher frequency of the pulsing, which is really resulting in this knife cut kind of a appearance of the sidewall. Here's a picture of a aperture made on one of these new lasers, and you can see the sidewalls are nice and smooth and you get a excellent shaped aperture.
Okay, Anna, thanks for that little history lesson. Going back to the last two methods, you mentioned electroforming and laser cutting. Why don't you walk us through those processes, as they are the most prevalent stencil manufacturing processes of today?
So in the electroforming process, a customer sends the stencil data, typically in Gerber format, which then gets processed to produce a film. The film is used to transfer the image to a mandrel, and the mandrel is placed in a chemical bath, and through an electrochemical process, nickel is grown on the mandrel, except for the locations where you want the apertures. Once the metal is of sufficient thickness, the mandrel is removed from the bath and the sheet of metal is peeled off the mandrel and mounted in a frame. In the laser cutting process, you start the same way. You get the Gerber data from the customer, prepare it, it is sent to the laser, the material is cut, and then mounted in a frame. With these machines, it's also possible to cut the stencil in the frame, which has advantages that we'll be discussing in a moment. So here we have a laser head. What happens there is the laser system really consists of two pieces, one a laser and the second one the movement system. And in order to get a good cut, the laser beam in this image comes from the top, then is focused onto the metal into a very tiny spot, approximately, depending on the laser, somewhere between 15 and 35 micron. The amount of laser power is not very high, but because the spot is so small where all this energy is concentrated, it easily cuts through the metal. Once the metal is liquid, it is blown away by either airflow or gas like oxygen. And to test the various laser systems, we have purchased these 14 stencils and made measurements, and we'll be reporting on that. I mentioned the movement system. The first original lasers, there was a large amount of mass to move, so it was a relatively slow process because it's difficult to accelerate and decelerate that much mass. Here's a picture, and in the horizontal axis, the x-axis, the drive system is underneath this gray, the dark area, and it moves the upper table, which also includes a piece of granite and the table that allows the movement in the y direction. When you add it all up, that is a lot of mass, and it really slows down the process. So the next step was to move the head of the laser in the x direction while the table was moving in the y direction. It reduced the amount of mass to be moved, so it allowed a little bit faster process. Then the final system in the most modern lasers, the head is the only part that moves, so it's a small amount of mass and it allows for fast movement. Together with that, these new lasers use diode pulsed lasers, which allow for a much higher frequency of pulsing. So together those two allow faster machining of the stencil. Here's an example of one of the new modern systems. It's much smaller than the picture you saw earlier. It gives the faster cutting speeds that I mentioned. Besides that, it's more accurate, approximately 4 micrometers. It has low vibration, so you get good straight cuts, and the machine is very easy to control. To show you a little bit what the laser does, it looks like this is moving relatively slow, but these are two large apertures that we're cutting to show you the cutting movements of the system. For small apertures, you'll find out that it's cutting really fast. So the two main factors that determine how effective the laser will be when it comes to producing precise and accurate stencils are the size and stability of the beam. If the beam fluctuates in size, the curve that it's cutting will be fluctuating in width, and your apertures will be having wavy sidewalls. Second one is the movement system of the machine. It has to, when, for example, you have a rectangular aperture, you want the machine to move in a straight direction and do a excellent fast acceleration and deceleration to allow it to go around the corners of a rectangle and give you good, nice looking corners. On the left side you see an image of a stencil that did not have those nice straight corners. So either the beam was unstable or the movement system was not very well controlled. On the right hand side there's an example of a rectangular aperture that is really rectangular.
Okay, thanks for covering that, Anna. So we've covered the actual processes themselves. Now, no matter which method you go with, whether your supplier is doing electroforming or laser cutting, there are other variables that can affect positional accuracy. And as we mentioned, they're tension and temperature. So why don't you tell us about how they affect stencil manufacturing?
Okay, first we'll show we're cutting a stencil as a sheet of metal. It is mounted in the machine, and typically it's tensioned in one direction to assure that it's taut and flat, so that the metal remains in the focal point of the laser beam. The tension here is typically around 18 newtons per centimeter. Once the stencil is finished and mounted in the frame, the mesh tension is about 35 newtons per centimeter, and it's both in X and Y direction. So in one direction you go from zero tension to 35 newtons per centimeter. When you have a 5 mil stencil or 125 micrometer stencil, that results in a strain of about 0.0131%. Over a distance of approximately 50 centimeters or 20 inches, that results in an elongation of 65 micrometers or 2.5 mil. On the other hand, if the stencil is cut in the frame, the tension is there before you start cutting, so there's no change in tension and no elongation. To show you how I can measure this, this was done on a stencil measurement system, and from on the left picture, from left to right, you can see that the distance is approximately 50 centimeters, and on the left side the apertures are located wrong in one direction. On the right hand side they're wrong in the other direction, and that's a significant error. On the right hand picture, this stencil is cut in a frame. It's the same stencil, same number of apertures, but you can see that the tendency, the general tendency of errors in location is horizontal over the full length of the stencil. The other item is temperature. Let's assume the stencil was cut in a facility where the temperature was a little bit higher than normal, say 25 degrees Celsius, and it's used in a beautiful environment where the temperature is well controlled and only 20 degrees Celsius, which is a typical room temperature. The coefficient of thermal expansion for steel is approximately 17 parts per million per degree Celsius. For nickel, it's a little bit less. But over a 50 centimeter distance, that means the steel will expand in approximately 42 micrometers. For nickel, it's only 32. By itself, that's not too much of a problem, 1.3 to 1.7 mil. But if we add up the problems that we talked about, the laser system itself has a positional accuracy of about 4 micrometers. We're talking about the most modern systems. Tension variations, we calculated about 65 micrometers, and temperature variations about 42. So when you add it all up, that's approximately 110 micrometers or 4 mil. So for fine pitch components with a 16 micrometer pitch, which means the apertures are spaced apart only 8 micrometers, half your solder brick is not on the pad. So how do we know then when a stencil is manufactured correctly before you use it? This particular image shows a scanning system, and it can scan a complete stencil in a few minutes. Then the data is fed into the computer, and the computer program lets me know where all the apertures are located. In this, what the scanner does, it shines a light through the stencil, and a number of line cameras are below the stencil, and the light forms a number of pixels. The blue on this particular picture are the apertures, and you can barely see it, but there's a green line around these apertures, which is the original data that this stencil was cut from. So this shows a very good alignment between data and final results. Of course, that's not always the case, and additionally, there may be debris still in the stencil, unless it's, of course, completely cleaned and has been used a little. This particular picture shows that there's something like a hair on the stencil or on the measurement table. The result of that is, for this particular aperture, it's a circular aperture, and the computer counts the number of pixels that were illuminated by the light above the stencil and calculates from that the centroid of this aperture. Because there are a number of missing pixels, the centroid is going to be too low. So that would indicate an error in location. However, I can easily see through visual determination of the data that this is not a laser problem or an aperture problem, it's a debris problem. So I can exclude this kind of data from my calculations or from my judgment on whether or not I have a good stencil.
Awesome. Thanks, Anna. So we just covered the processes that you can go through, and we've also discussed the variables and how they affect positional accuracy. Now, you actually measured 14 stencils to determine how the 4 M's really impact stencil manufacturing accuracy. So walk us through your results and tell us what you've determined is the best way to manufacture SMD stencil.
So after the scanner has done its job, if I want to, I can extract all the data from the scanner and put it in a spreadsheet. When you look at this particular picture, the jagged blue line is the result of the actual data that came from the scanner. Only the portions that I used out of the data after I excluded some of the bad images. The black line is the bell curve that this data fits in. Then the purple lines are the plus or minus 3 sigma. And for this particular test, I set a spec limit of plus or minus 10 micrometers. And you can see that the bell curve, the black line, fits within the 3 sigma lines that we have here. And so this particular stencil has a CP that is better than 1. To show you some of the difference, I have here on the left side a stencil that was cut in the frame and a stencil that was cut as a sheet done on the same machine. And you can clearly see that the stencil that was cut in the sheet, the data is spread out much farther, which means that your CP value has gone way down. On the right-hand side, I have 2 curves on the same stencil but now cut on 2 different machines, and we see the same kind of results. One, the tall peak, is the good laser or the better laser. It gives you a very narrow distribution of aperture locations, while the other one shows a very wide distribution, and again it means that your CP is much lower. When I take the data from all 14 stencils, the blue bars show the CP value for all the stencils. The yellow ones are the ones that were cut in the sheet. So this clearly shows that a stencil cut in a frame gives you a better distribution of errors for location than if the stencil was cut as a sheet. On the left side, you can see the CP ranges. In addition, I calculated the error range for each of these stencils, and those are the brown bars. On the right-hand side is the scale for that. And you can see the worst stencil for both very low CP, it has a high error range, in this instance about 180 micrometers, which means a 7 mil error. Again, when you have a stencil that includes 16 micrometer pitches, 16 mil pitches, that means the apertures are spaced about 8 mil apart. With a 7 mil error in location, you are now printing between pads on the board instead of on the board, on the pads. And that's for stencils for a perfect board. We haven't even talked yet about the accuracy or precision of the location of the pads on the board. My personal experience has been that I've seen some very bad boards where a number of apertures were 11 mil away from where they were located. So that's an additional headache to consider. Of course, the other part of printing is the paste release, and I added a graph here that shows paste release for a number of different metals that have been used and are available. The light blue line is basically the original metal that was being used for most stencils. When you look at the area ratio, which is the ratio between the wall area and the pad area that is being exposed by the aperture, the more wall area you have, the more likely it is that paste brick stays in the aperture. The pad, on the other hand, sucks the paste out of the aperture. So for a ratio of 0.67, it was typically considered you would get good paste release. And you see the vertical yellow line intersecting with the blue line, which gives you the percentage of paste that gets deposited on the board and which is considered acceptable. When you follow the horizontal black line, you see it intersects with the red line, brighter red line, and at that point the area ratio is almost 0.5, as low as 0.5. That means that you can use much smaller apertures and still get the same percentage of paste release. So choosing the right metal for your stencil is an additional consideration for a good stencil. So the stencil positional accuracy is a function of the manufacturing process. With the CP analysis, we have shown that if you have the right machines and the machines are well maintained and used, you get an excellent CP for aperture location. Additionally, the varying tension and varying temperatures, you have to make sure that those are all also well controlled, and therefore I can conclude that using the best laser and cutting the stencil in the frame gives you the best results for positional accuracy. So the follow-up conclusion of that is you have to know the vendor of your stencils, and you have to know how and what he is doing and what kind of equipment he is using to make his stencils.
All right, so with our two conclusions there, we've reached our large conclusion. And so I just wanted to let you know that a recording of this presentation and a copy of the slides will be sent to you soon. But I wanted to thank everyone for attending today, this morning. After the long weekend, it can be hard to get back to work. And so I appreciate everyone stopping by. Anna, I wanted to thank you once again for lending me some of your wisdom here. If you have any more questions for either Anna or myself about SMT stencils, you can contact us by any of the methods as seen on your screen. So I do recommend phoning or emailing is the quickest option. Snail mail may take a while. And we're actually going to field questions in just a moment. So if you have any questions, get them in now. But while you're submitting your questions, I also wanted to mention that if you would like more information on this topic, you can copy down the URL on your screen. There you can find the white paper that this webinar was based off of. It has more information than what we've shown here. And in general, if you go to lpkfusa.com/SMT stencil, you'll find a lot more information about solutions for the SMT stencil process, including another white paper, and we have some spec data up there that you might find interesting. But we'll go ahead and give another minute or two for questions. So I'll just sit tight for a minute and we'll see what we got. All right, so it looks like we got a good amount of questions. First question comes from Jeff Hempton, and he asks, can you give your opinion, Anna, on wall integrity from different laser types and your thoughts on electropolishing?
Yes, I can. But you probably want to know what my opinion is. Recently I did a study where I imaged various walls of these stencils. So I cut samples out and under the microscope took images. It is very difficult to predict based on a visual inspection of the wall how it will behave when it comes to paste release. Of course, in the extreme cases, when the wall is very rough with mountains and valleys, you know it's not going to be as good. But in most cases, it's difficult. When you think about it, the most common solder paste has 30 micron solder balls, and it takes a really rough surface to catch one of those and prevent it from being released. However, one of the graphs that was in the presentation showed paste release for various metals. So when you look at that graph, you can already make a determination that some of these metals work better than others. Electropolishing, that has been disagreed upon for a long, long time. My personal experience was that electropolishing didn't do enough good to warrant $50 extra in cost of the stencil. I have seen some reports that indicated there was an improvement with electropolishing. I also have seen reports that said there was no improvement with electropolishing. So from my own time as a manufacturer of stencils, I have never recommended anybody to pay for electropolishing. And personally, I didn't like to work with chemicals, so I did not make that option available at all.
Awesome. Thanks, Anna. So we have a few more questions. So our next question is from Oded, and he asks, how do you rank nickel material cut by laser? And I think he's asking it in context of nickel versus steel. So Anna, how does you rank nickel versus steel cut by laser?
Again, that going back to that same graph, it shows one of these as being a sheet of nickel cut on the laser. And again, the best results for paste release for these metals came from the very fine grain stainless steel that has become available over the last 2-3 years. So going to a nickel sheet increases the cost of the stencil, but it does not gain you all the advantages that you can get from other metals.
Awesome. Very pithy and astute, Anna. So we have a question in from Eric Bastow, who has a few questions. First of which, he says, at what point does a laser cut stencil lose its advantage over an E-form stencil in terms of cost? Anna, you're definitely more prepared to answer this question than I am.
From my knowledge, laser cut stencil never loses its competitiveness over E-form stencil when it comes to cost. Laser cut stencils are always less expensive from what I have seen. And when you look again at the paste release graphs and at the graph that shows the CP for the various metals, an electroform stencil is prepared before it is mounted in a frame. So that on this graph it means it's one of the yellow bars and the blue bars win over the yellow bars. So for a very large stencil, an electroform stencil is not an advantage over a laser cut stencil.
Okay, thanks. And looks like Eric has one more question. Let me pull it up really quick. Okay, so Eric asks finally, what is the status of nano coatings for stencils? Anna.
Nano coating has become available only recently, and I have not done any testing on a stencil that was prepared with nano coating, but the initial indicators are it helps in paste release. I know a paper that was published in Germany that showed significant improvements. I have not seen significant improvements, but some improvements from nano coating. So I have no numeric values yet on nano coating versus non-nano coated stencils.
All right. Well, I think that's all the questions we got on in. So once again, I'd like to thank everyone for attending. We'll be following up with you soon, and feel free to let us know if you have any more questions by email. But yeah, thanks everyone, and have a good day.